Hello, my name is John Lynch, and I'm a software developer with Side Effects Software. This masterclass is about flip workflow enhancements in Houdini 15. So for Houdini 15, we've added a set of tools for dealing with the output of very large-scale flip simulations, like the one you see here. This one's about 120 million particles, and simulations of this size or even larger are becoming very common in production. So the tools that we've added are to help deal with the very large data sets that can be created by these simulations, tools to help surface these with one node, and to create secondary elements as well. So to that end, we've added a data compression node that reduces the amount of data that actually has to be stored to disk in the first place to represent the flip simulation. We've created a new surfacing node that can take the output of this flip particle and the compressed output of this flip simulation and create a high quality surface like the one you see here. It has common operations for doing things like smoothing and filtering the mesh before rendering. We've added some features to the whitewater workflow to make it quicker and more lightweight when dealing with these very large scale simulations. And we've added some features to the flip solver itself to help create these large scale simulations, and also to output some data that's very useful for surfacing and shading. So what is flip data compression, and why is it so important, and particularly for Houdini 15? So for Houdini 15, we've significantly upgraded the distribution capabilities of the flip solver. So we've always been able to distribute flip simulations across multiple machines, but it couldn't really handle tank simulations like the one you see here. So now, as you can see, we've actually colored the different slices of this simulation according to which nodes the simulation ran on. So this has actually been split across 4 different machines. Each one had about 30 million particles in the simulation. So with these new distribution features, we can create particularly large-scale simulations, and we need ways to deal with all the data produced. I'm not going to talk too much about distribution in this class. We're actually going to have a separate master class all about distribution. So the issue is creating all this data can be slow to load and display in the viewport. It takes a lot of disk space, and loading it over a network can take a large amount of bandwidth as well. So how does data compression work from sort of a high level? We start out with very dense data that comes out of the flip solver, and we want to turn it into sparse data in SOPs. So we can start with the flip particles, which are the main simulation representation. They have both a representation of where the fluid is at any given point, and also a number of attributes that define the simulation. Things like velocity, density, possibly viscosity, if the viscosity solver isn't included. And so we're going to use only a thin layer of these particles after compression to get surface detail. We also, within the flip solver, are creating secondary volumes or fields, both a sign distance function, sign distance field for the surface, and a vector field for the velocity. And these are used in the solve process for things like the pressure solve and advection of the particles within the velocity field. With the whitewater solver, we typically will save these secondary fields to disk as well, these secondary volumes to disk, because it's so useful for doing these secondary elements like whitewater. You can use the surface sign distance field for depth testing, and also and the vector field for velocity field for things like advecting the secondary particles around with the fluid. So with the compressed data output, we're going to actually use these fields to fill in the missing data that we've discarded when we got rid of all those other particles. So everywhere that we don't have particle data anymore, we will fill in with volume data. So here's an example that we'll be looking at in the Houdini viewport in just a second. This is about 11 million particles, which is not very big these days by production standards. It also includes, you can't see it here, but about 14 million voxels in the surface and velocity fields. And saved to disk, this is about 52 gigabytes compressed. And by compressed in this case, I mean losslessly compressed with our BLOSC format, which is, you can think of as like a gzip or something like that. And so we want to compress that to a format that can look like this in the viewport, where we've discarded a large number of the particles. We're down to about 1.3 million particles, we are storing about half of the amount of voxels, and we're also storing those to disk as 16-bit. So we get about a 4x reduction in data there, and overall we get about a 6x reduction in the amount of data we have to store to disk. And importantly, you can actually scrub through these simulations for previews. You can maybe get a few frames a second with even very large scale simulations, which starts to make it much more effective to preview and to do secondary elements and secondary simulations on top of those simulations. So let's talk about the steps that are involved in doing this compression and look at how that looks in the Houdini viewport. Okay, so this is this simulation in the Houdini viewport, and this network view over here shows the default setup from the flip shelf tools. It's fairly similar to the one from Houdini 14. One difference is actually all the surfacing operations are encapsulated into this one node here. We also have a preview node, which is we'll go through in just a second, and it adds, of course, this fluid compress node, which is sort of the point of this part of the talk. This import fluid tank here is similar to the one that's in Houdini 14, and typically it's set up to use the flip preset here, which imports geometry, surface, and velocity fields. So if we look at this data, we've got, this is the one where we've got almost 11 million points and almost 14 million voxels. And if we play through this, you'll see that we load in maybe 2 to 3 seconds a frame. Actually a little under 2, not too bad. So then we run that through this fluid compress node that we'll go through and and then we cache the results of that. And so typically, in this case, I've actually saved the uncompressed fluid from this cache node here, and then also the compressed cache. Typically, you would not do that. You would not save the uncompressed fluid, since the whole point is to save disk space. So just for demonstration purposes, I've saved part of the uncompressed simulation. But typically, this node down here is what you'll actually render to disk, the compressed cache. So you'll see here we have this sort of different looking save here. We have all these kind of little tile looking things representing the simulation, and the kind of important thing that we're talking about is you can pretty much scrub through this. And this is also just loading off the disk, but it's getting 3, and then some points I think later on it gets up to around 4 or 5 frames a second. So what exactly are we seeing here, and how did that uncompressed data turn into this? So if we look at the fluid compressed node here, so it has particle operations and volume operations, and the particle operations are that culling of the particles that we talked about to keep just the surface detail. So if I turn that off, this is actually going back to the full data set again. And so what we first do is we cull the particles to within basically 4 particles worth of data at the surface. So we are left with this very thin layer of surface detail particles that we're going to be using for surfacing and whitewater emission and that sort of thing. So you can see that we're basically going from 11 million particles down to this here it has about 1.7 million. And then we have an additional, and I should say we also have a very explicit set of attributes that we're going to keep from the simulation. So the most important, the typical ones, are velocity, p-scale, which is the size of the particle, and possibly ID, droplet, all these other things. So everything, velocity and p-scale are sort of the standard attributes. Everything to the right of that, all of these over here, are things that are optionally created on the flip solver. You have to enable options on the flip solver to create these attributes. So it's assumed that if we create those, we actually want to save them to disk. So we explicitly keep this list, and everything else will get deleted. And then we have this important option here, which is pack particles. So if we turn this on, this is what gives us that view of the sort of tiled view of it. What's happening here is we're actually partitioning all of the particles into tiles. And then we're saving, and each tile will have about roughly 4,000 particles in it. And we're then saving, we're converting each tile into a packed primitive. And a packed primitive in Houdini is an individual primitive that can be comprised of as many other primitives or points as you like, and that could actually even be hierarchical. But in this case, it's fairly simple. It's just a single primitive that is comprised of all the points in that tile. So we're going from however many millions of points typically down to a much smaller number, in this case 1800 primitives, where each one of those primitives contains a certain number of points. What's also interesting about that is we have delay load capability for packed primitives. So that means that when we save these to disk, we have this delay load geometry setting here. And what that means is we won't actually load any of these points. We won't load all of the detail within each packed primitive until we absolutely need it. So when we're scrubbing through this, what we're loading from disk is just bounding box information. So that's all we're getting out of this this fluid compress, is we're seeing the particles stored in these packed primitives, and we're displaying the bounding box information. So this becomes a pretty useful view for just saying, all right, where in the simulation do we want to start focusing our attention? So if you can sort of scrub through the different parts of it and then start working here, and we'll see how you actually then can look at the original simulation data in just a second. So then the other operations in fluid compress are the volume related ones. So what we're doing here is we're limiting the bandwidth. So we're essentially converting this fairly dense data here. So if I'm middle clicking on the original uncompressed data set, and you can see we've got around 14 million voxels, maybe a little more, in these 4 different native Houdini volumes. And what we're doing here is converting them to sparse volumes, sparse VDBs actually, and limiting the bandwidth, turning them into narrow bandwidth VDBs. Before we save to disk, we're also toggling on this write 16-bit float. So we are saving the data to disk as 16-bit floats, which basically halves the size of the data again. And it turns out that for the kind of SDF operations and filtering that we're doing and the advection that we're doing, 16-bit data turns out to be plenty. So this defaults to on because it's another nice memory disk save. So the output of this is actually those packed geometries that we were talking about, and then 2 VDBs. So we convert those 3 velocity native volumes into a VDB, a velocity vector field, that is also just sort of easier to work with. So we have 2 VDBs coming out of this, and then the packed geometries. So the other thing worth looking at is if you look at the amount of memory here, we've got about 282 megabytes of memory used for the uncompressed data, and then about 40 megabytes for the compressed. So again, we're 6 or 7 times smaller. The other interesting thing to notice here is we've got these detail level attributes that all start with fluid compress, and these are actually written out by this fluid compress node, and they signal to any downstream nodes, for instance the surfacing node or whitewater source, that this data is compressed, and it keeps things like the particle bandwidth, which essentially says how deep into the fluid we've kept particles. So anything below that in the fluid needs to be filled in with volumetric data. So most of these new nodes, these existing nodes and new nodes that can deal with compressed data can also deal with uncompressed data. They'll just notice that these attributes are missing. The other thing that's useful is we get a list, or we keep track of the original number of uncompressed particles, and then also the number of compressed particles, which is just kind of useful to get a sense of scale for your simulation size. And these are actually saved to the header part of any file that's written to disk, which is kind of nice. So you can do things like go to use the gstat command line, and this will write out just the header information from this file. So this is one of these compressed simulation files written to disk. It's about 40 megabytes, but it reads very quickly because all it's doing is looking at the header. You can see we have the information here of how big the original simulation was and how much we've compressed it to. And then finally, the other interesting thing about fluid compress is it's just a digital asset, and actually not even that complicated as these things go. So if you're curious about how the inner workings work, you can go in and look at all these details to find out exactly what's going on there. Okay, so again, this is kind of an interesting view to be able to scrub through your simulation, but it doesn't really let you see the detail of the original simulation. So the new particle fluid surfacer has a lot of interesting outputs that we'll go through in just a little bit, but it also has these preview outputs, and that's what we're looking at here. So there's actually a separate node set up that's just basically for previewing what your original flip simulation looked like. So this parameter here has all the different outputs of the particle fluid surface node, and the first three here are all previews. So real quick, we'll go through what those are. This is just the particles that are kept from the simulation. You'll see this plays back a bit slower, but not too bad. But this lets you look at the surface detail that's being kept from the simulation. The only problem with this is kind of a preview is that you can see through the particles. They're sort of sparse enough that you can see through, and you can do things like increase the particle size, but we thought that it would be useful to have this sort of combined view here, which is actually the particles on top and then an inset version of the surface STF, the one that comes from the simulation, below it. So especially if you turn on the closed boundaries, you get what looks like basically you're using the surface field to fill in the depth below the particles. So you get something that looks pretty much like the uncompressed data set. So just real quickly to show what that looks like, this is a flip book of the full uncompressed data set. So you can see we've got all these particles along the bottom here that are deep below the surface. And then if you use that other preview mode, this is one where we've thrown away all those upper particles, but we're using the surface field to fill in the depth down here. So you can see it's a fairly good estimation of the original uncompressed data set just in terms of flipbooking. So it's useful as a way to kind of get a good view of the particle simulation, what it looks like, similar to flipbooking the original uncompressed data set. And then finally, the other preview mode is actually just the compressed fluid surface itself. And this is actually the fastest preview mode. So all this is doing here is meshing the surface field as it comes out of the flip simulation. And what's kind of nice about this is that it's actually not loading any of the particles at all. So because it's only referencing the volumes, those are the only things that get loaded off of disk, and the particles themselves never get loaded and just stay on disk. So this is actually probably typically the fastest playback method, just as a way to kind of get a view of what your simulation looks like. Yet it can also be useful if you're doing things like whitewater simulations, and you want to be able to have an idea of where the surface actually exists, and you want to be able to see bubbles underneath. We'll see an example of this later. It can be a pretty useful way of putting the whitewater in context with the fluid surface. So finally, the one other thing I wanted to show is another nice element we get from this delay loading of the particles is we can actually use these regions tabs to sort of focus in on particular parts of the simulation. So probably the easiest way to adjust this is to just hit enter in the viewport here, and then we get these handles that let us kind of focus in on. Let's show so we can see the other collision objects. So let's say we wanted to just focus in on the part where the box is interacting with the fluid simulation. So we can actually focus in here, and as we're loading this, you'll notice it's actually loading a lot faster. That's because we're only loading in the particles that exist in this bounding box. So the other particles don't ever actually get loaded in from disk. So this can be kind of a nice way to focus, especially with very large simulations, if you want to just look at individual little areas to either work on surfacing or work on whitewater emission or whatever. It can be a much faster way to work with a large data set. And this works for actually all the surfacing modes and all the preview modes as well. This can also be used with cameras. So if we've got a second camera here that has a fairly close-up view, and if we let's turn this off for now, and so we're loading in the full data set, and then if we turn on the camera, you'll notice that we're actually only loading the particles within the frustum. So again, if you've got a dynamic camera or a close-up camera in a large simulation, you can actually work on previewing this and looking at your data without loading the full data representation off the disk. So just to see a larger scale example of this, this is the original sim that I was showing at the beginning of the class, and this was, like I said, about 120 million particles. Here we've just sort of attached the bounding box to, this is our Crag demo character, so we've attached the region bounding box to him to sort of focus in on how the water looks right around his legs and just sort of how he interacts with it. And if we wanted to work on surfacing there or generating very particular secondary elements, we could do that. And if you notice down here, we're only loading in about 3 or 4 million particles per frame here, down from the original simulation of about 120 million. So as you can imagine, it's just a lot faster to work with as a way to preview a very specific part of the simulation. Okay, so we've looked at ways to compress the fluid data before saving to disk and to preview that data and get a view of, for instance, the thin layer of particles at the surface here. And we want to look now at how we can use the 2.0 version of the particle fluid surface node to give us a mesh that we can render. So something like this. And importantly, if you look at that wireframe, you'll see that there's a lot of detail here in the kind of splashy area, a lot of polygon detail, and then down here in the area where the fluid hasn't really moved much yet, there's not many polygons, and importantly, it's extremely flat. So this will render really nicely, and we want to look at ways that we can achieve that effect. So real quickly, just to look at what this final render will look like with an opaque material, and you can see here we've got all this right underneath the spinning box where there's lots of detail. You still maintain all this kind of very high-res swirls and splashes and stuff, but down on this other end, it's much smoother, and particularly in the early part, it's sort of completely smooth. And just to have another view of this with sort of a more typical liquid-looking shader, you might notice here there's some sort of cloudiness at the beginning. This is actually using vorticity to influence the shading, which we can look at a little bit later. It's sort of a decaying vorticity attribute. But again, you've got some very nice, smooth water down here with lots of detail right underneath where the splashing is going on. So real quickly, to look at what the shelf tools used to set up in Houdini 14, the surfacing workflow was essentially to run through VDB from particle fluid and then we would convert it to to a polygon soup here typically, and then we would transfer like a velocity attribute from the original points onto the mesh, and then send this out to render. And this would give us velocity motion blur, but it's a little unwieldy just because it's 3 nodes here, and if you added more nodes, if you wanted to filter anything, you'd put it in, but you put a VDB smooth here, or if you wanted to, for instance, subtract out the collision volumes, maybe a VDB combine. So you could have a series of nodes here that would be your sort of surfacing workflow. And we can still do some of that, and I'll show you how that works. But for the moment, we can look at how a lot of that is encapsulated into this one node here. So if we look at this is a particle fluid surface set to the defaults. So this average position method here, basically it starts out doing the same exact VDB from particle fluid internally, I should say. This is a digital asset, just like the fluid compressed node. So it's a bit more complicated, but it's a fair bit more complicated. But if you want to come and look inside, once you can do that. This average position method here is the one from VDB from particle fluid. So really, with the default settings, we still use the same initial node. We're handling the compressed input. That's what this union compressed fluid surface option does here. And then we're handling that attribute transfer all within this one node. So in its simplest form, the particle fluid surface node is just an encapsulation of those other nodes from the Houdini 14 workflow in one place. But there are a lot of other capabilities we'll go through in just a second. But there are lots of cases where this default setup is going to be plenty for any sort of surfacing needs. Really want a nice smooth mesh with velocity and whatever attributes that you might need for shading transferred to it, and the defaults for the particle fluid surface should meet those needs in a lot of cases. There's a lot of these other capabilities are for when you really want more control, very explicit control over exactly what the surface looks like, and even control over having different sort of amounts of smoothing and filtering in different areas of the mesh. So that the renders we just looked at actually use a fairly customized version of particle fluid surface, so to get a very specific look. So let's go through on how exactly that comes about. So this is a particle fluid surface set to where I've turned off a whole lot of the features, just so we can step through turning them on one by one. So here we have, you'll notice we've moved to the spherical method. This is actually internally, this does a VDB from particles, which is distinct from VDB from particle fluid. And VDB from particle fluid tries to smooth out the initial particle representation of the fluid by adding in additional ghost particles or particles in between the original particles to smooth out the fluid surface. VDB from particles in this spherical method just puts little spheres around each particle. It does it very quickly, but that's all it does. So you pretty much always need to do some post-processing after the fact so that you can get exactly the look you want. On the other hand, this gives you a great deal of control, so you sort of know exactly what you're getting out of it. You're getting just all these little spheres around the particles, so it's a good way to start working with if you want very exact control over how the surface is going to look in each little part of the simulation. So for the moment, I've got this union compressed fluid surface off. If we go look at what we've got here, this is actually, if we go back to the particles, we see the particles here. And this really is just a surfaced version of those particles. So you'll see it's a very thin layer that's just been surfaced, and it doesn't look like it has any depth to it. So what this union compressed fluid surface does is it actually will take that surface field that came out from the fluid compressed node from the original flip simulation, and it will use it to fill in the depth when it's doing the surfacing. So if we turn that on, basically we'll offset and then union in that surface field before we do any of the surfacing. And that will give us the depth that we need so that we can actually get the full surface. So just so we can see it real quick, I'll turn on the closed boundaries. And you'll see that we actually get the depth back along here. So that if we sort of go in here or turn on that we've got the full representation of the fluid here. So even though we only kept that really thin layer of particles, by using the volume, we can restore all of that data underneath the water. Okay, but if we look at this closely, we can see that we've still got a lot of bumpiness to the surface. So this is where we start really needing some post-processing to be done from that initial VDB from particles. So if we go to this filtering tab, these first few options here, particularly this dilate and erode, by default these are actually tied together. So if you turn on one, you get both. And this is what's generally or often referred to as a closing operation. So what it'll do is it'll actually expand the surface outward, the VDB sign distance field outward, and then just erode it back together. But what that effectively does is it'll close a lot of the spaces between individual particles, and then when you erode back down, you've essentially connected a lot of those particles that are already close together. You can control how far out how many voxels out you want to do that. And the more you do, the more you'll do that closing, and you'll generally smooth out the surface. And another effective technique can be to actually do a smooth on that dilated surface. So you'll dilate outwards the surface, you'll do another smoothing on it, and then you'll erode it back to where it began. In particular, these mean curvature flow and mean and Laplacian flow are second order smoothing operations that are actually do a nice job of adding some smoothing without losing too much small detail. So for sort of a default, this starts to give you a really nice surface, just starting from that VDB from particles. But if we look at the wireframe, we've still got a lot of data down here and a lot of polygons down here because it's not sort of completely smooth. We have lots of detail here as well where the splash is going on, but that's what we want. So we have some adaptivity going on down here because there is less curvature, but not as much as we would like. So we're going to look at doing some additional smoothing. So that's what this final smooth operation is for, and here it's set to a Gaussian, which is a fairly strong filtering operation. And if you applied it to the entire, actually let's go ahead and look at that. Okay, so if we turn on this final smooth with this Gaussian, you'll see that so in these areas where we've got all these nice fine ripples and splashes going on, that it'll actually smooth almost all of those out. So it's really way too strong a smoothing operation. We do, of course, get a nice flat area down here, flat surface down here, but we've lost a lot of the detail we had in this splashy area. So what we want to look at doing is creating a spatially varying mask. So essentially a mask that will leave, say that you can do lots of filtering down here where not much is going on, but don't do any filtering in this area where there's interesting behavior. So to create that mask, we can use all these different options. So we'll look at that real quick. So I've got a lot of these options already set up in ways that will work for this particular sim. And so if we turn on this visualize mask, I've actually got a visualizer, on speed here. So if I turn that off, I can see what the mask is looking like. So what this is doing is mapping the velocity of the fluid, the vorticity of the fluid, and then an offset from the collision object. So if we look at the collision objects, we can see that. And then combining those all together to make up this mask. And everywhere there is purple will not be filtered, will not get any smoothing, and everywhere is sort of red or orange will get the full smoothing effect. So by limiting the filtering to areas where there's very little velocity or very little vorticity, and there's various different ways to combine these different criteria, we can control where we actually do any of that smoothing. So if we can apply that mask to any of these filtering operations, but it's typically most effective applied to a final smooth like this. So if we turn on the smoothing for that final smooth Gaussian, we will find that all of the detail here gets kept, but down here we're still doing the full smooth, so we'll get that nice smooth surface that we wanted before. So now we can see we've got all the detail in the mesh here, but we've still got the smooth surface down here. And if we can go back to this, so we'll see we were getting basically what we had from that cached out version I was showing before. And then there's some region operations we can do, like subtracting the collision volumes. So what that does is after doing all these different volumetric operations and creating internally a VDB, it just does it creates a VDB from these collisions that are coming in here and subtracts them out from the mesh. So all that really gives you is just a really nice smooth layer between wherever, like, so you can see that we've got this really flat area here between the collision object, which can be useful, and you can determine how much offset you want from those collision objects when you're doing that subtraction. And then finally, if we want, we can close the boundaries as we have looked at before, which can be useful if you're rendering a tank. I mean, in production, you probably don't often want to actually see the boundaries of the tank, but for testing, it can be pretty useful and for just sort of having a full volumetric object for rendering. It can be useful as well. And finally, just to go through showing some of the region operations. So we looked at this a little bit when we were talking about just previewing the output of the simulation. But it can be useful to, when you're changing all these, or iterating over all of these different settings, it can be useful to restrict the surfacing to just a small part of the actual fluid so that you can better tweak the parameters without waiting for the entire fluid to surface. So it's the same setup where we can hit enter in the viewport and adjust. I've got the update mode to set to on mouse up here. So this is going to be this won't update until I've actually let go of the handle. And okay, so if we look at this, it's the same fact is true for this as well as for previewing in terms of when we're restricted to a region, we're not loading any of the particles from the rest of the fluid, which makes this whole operation a lot faster. So you're only really working with this small area here. And in particular, this can be a good way to tweak this mask. So if we turn off the mask smoothing here, so this can get really fast. So actually, let's go back to auto. I'm sorry. Go back to auto update, and so we can start changing some of the values for speed, and you can see these are changing, and you actually get a fairly decent operation to be able to tweak these values and visualize just where the mask should be and where filtering is going to happen. So if you notice, we actually have the smoothing off. We only have the visualization on. So this final smooth, I mean. So we can tweak just by looking at the colors, tweak where the smoothing is going to happen and where it's not with these different values. And then when we finally are happy with our settings, then we can turn on this final smooth, and it'll actually do the more expensive final smooth operation using these mask values that we've decided on. Then we can go back to our speed visualization. And so this is just a nice way to work when we're tweaking values. And again, the camera can be used as well if we only want to surface a subset of the fluid simulation that's actually visible within the surface frustum. And then finally, just to go through a few last features, the third input here is actually a mask volumes input. So if you want to create any sort of custom volumes to control the masking, you can paint them or however you want to do it. If the criteria that are on the filtering tab here aren't enough, you can sort of create however you want to, or if you want even more control than that, you can actually set the output to just be the surface VDB. So this is actually the raw VDB, although it will have been the surface field will have been unioned in from the simulation, so you'll have full depth and everything. But if you want to basically, if you want to go ahead and do all of your output customization from there, so do a workflow that looks more similar to Houdini 14, where you will have separate nodes that you put down to do filtering and that sort of thing, and then at the end you finally convert to polygons. You can work that way as well. Okay, so I wanted to talk about whitewater now and some enhancements we've made to that workflow. In particular, dealing with reseeding the compressed fluid. So we've come up with a very sparse data format for our fluid, but we need to be able to create whitewater even in deep areas of the fluid. So in an example like this one, you've got lots of little pockets of whitewater that need to be generated, and they're very important for the look. So it needs to, in other words, you couldn't get away with just foam on the surface. You actually need those bubbles that are kind of down underneath the surface. That sort of foam aeration type bubbles is really important for this look. So if we don't have all those particles, how do we regenerate them, basically? Some tools we've added for distributing a simulation by camera region. So this simulation, I'll show a visualization of this later, but we're actually distributing this across 4 different machines. The whitewater simulation, actually as well as the flip simulation, but the whitewater simulation is distributed working backwards away from the camera. So there's actually 4 different slices being simulated on 4 different machines. We've got some ways to reduce the amount of disk space you have to use for caching your whitewater emitters. And we've also reduced the amount of memory that's being used as you import the simulation fields into the whitewater for things like advection and surface depth testing. So we have the same problem here that we had for surfacing, which is that we've got this very thin layer of particles here. So how do we come up with the secondary elements that are deep within the fluid? How do we have these bubbles and aeration looking things that start deep below the surface even though we don't have any particles there? So to understand that, we need to look a little bit about what the whitewater emission workflow looks like. So typically it'll take flip particles as the input to the whitewater source node, which is responsible for creating these emitter particles in the first place. We will do a quick first call, killing all the particles that don't match the depth and velocity criteria. So that basically means we'll have a limit possibly on depth. There's a limit by depth parameter you can see here, and then a speed range for the fluid, where anything below that's outside that range, really anything below the minimum speed, we can go ahead and throw away those particles, because we know that we'll never be able to generate any whitewater from areas where the fluid's moving that slowly. The particles that are left over, we then will sample things like acceleration, vorticity, and curvature from the fluid simulation, and then we'll map those to the probability of emitting whitewater. And then anything that once that probability mapping is being done, if they have no chance of emitting any whitewater, we'll do a final cull of those particles. So what's left over are the particles that have some chance of emitting whitewater particles. So if we're going to create particles or whitewater particles deep within the surface, we need to do some reseeding of candidate particles deep within the fluid, and then send those into step 3 here, when we're about to start sampling the acceleration of vorticity. So the question becomes, how do we efficiently seed particles throughout this fluid that could be very large and span across a very uneven domain? So, for instance, in that river simulation, it's not axis aligned in any way. There's lots of different levels, and it encompasses a large amount of space. So what we're seeing here is actually a mapping of that initial depth and velocity criteria to a fog volume. So everywhere that there is density is actually where the fluid is moving quickly enough or is deep enough to potentially emit whitewater. So this is just using those surface fields. Those simulation fields. So using the velocity field directly from the simulation, and measuring it and mapping it to sort of a 0 to 1 density. So the squares that you're seeing here are the active tiles. So a VDB has the concept of what part of a volume is actually active, where is there actual data that we care about. So by mapping that first level criteria from sort of 0 to 1, we're actually setting up a set of active areas within the fluid that could potentially have whitewater emitted. And so even though we're looking at areas that are deep within the surface, even though we don't have any particles there, we can seed into just these active areas very efficiently and use them as the candidate particles for then sampling the different further emission criteria. And this is what this looks like. So this isn't an actual simulation. This is just showing the whitewater emission candidates. So everything that's the typical blue and white here are the ones that are working with that thin layer of particles that we get from the compressed fluid. Everything that's sort of pink or purple are actually reseeded particles that are down beneath the surface and are giving us that sort of aeration and bubble stuff, even though we don't have any of the original flip particles at this level. We've reseeded them efficiently down within the surface. So let's look at how this whitewater emission works from within the viewport. So we've got the output of whitewater source here, which is the node responsible for creating those candidate whitewater emission points. And if we look at what our main simulation looks like, our flip simulation and the collision object, we can see we've got candidate whitewater sort of down here below the surface. And actually this surface here is actually that preview, that compressed fluid surface preview that we were talking about earlier as being a good way to sort of get a good preview of where the final surface is going to be. So if we turn off that recede compressed fluid option that I was just describing, you'll see we lose a lot of that data deep within the surface, deep within the water, I mean. Turning it back on. So all this stuff is what we're getting, the sort of bubbles and aeration that we're getting from the whitewater, which we really need in a lot of cases for sort of realistic looking bubbles and foam. So let's look a little closer at how that works. So if we dive into this asset, so this the whitewater source is just another digital asset, and there's another subnet in here that takes care of reseeding points. And so this is kind of the visualization I showed before. This is that velocity field. Let's turn this off for just a second. So this is that 0 to 1 velocity field. So everywhere that it is deep or fast enough here are places that we can possibly generate whitewater emission below the surface. So you'll notice that this fog volume is actually already below the surface. So we're assuming that everything at the surface is going to be taken care of by the points themselves, the flip points themselves, and we only need to reseed here down below the surface. And then these are the active voxels that I was talking about earlier. If we move forward, we see there aren't too many left as the simulation slows down. So the really important point here, and what's new for Houdini 15, is the points from volume node here has a new option, this construction method up here, which it says sparse volume. So the way that the points from volume used to work is after you input the volume, it would take the bounding box of it and would fill the entire bounding box with points, and then it would just call out the ones where there's insufficient density or where it was not within the assigned distance field. Which was fine, but would not work for very large or sparse input volumes. Which, for instance, in that river simulation we saw earlier, could be we would have a very large and very sparse input volume because we had all those different levels of rocks where the water was flowing down. So we need a faster way and a more memory efficient way to generate new points. So that's what this new sparse volume method will do. It actually runs vex on just these active volumes, just these active voxels, and generates points only within them. So this is very efficient for large and sparse fields, which is necessary because that's what we're going to have for reseeding these simulations. So this sparse volume method is new in Houdini 15 and is really effective for reseeding within sparse input volume. And so I should point out, if you only care about top level whitewater, if you only really need whitewater at the very top, and maybe you're turning on this limit by depth option anyway, it might be faster to just turn off reseed compressed fluid, and then you'll only get whitewater at the very top to begin with, and it's a bit faster because it doesn't have to reseed within the surface. So the other interesting thing for Houdini 15 is you'll notice here this is how the shelf tool set up the whitewater sourcing now in 15, and you'll notice this output points only option, which has been on the whitewater source, is now toggled on by default. And what that means is that the output of this source node is going to be only points, no volumes. So prior to Houdini 15, the way you would typically work is you would send a flip simulation into this whitewater source node, and the output would be both all of these candidate particles, these emission particles, but also the original simulation volumes from the flip sim itself. And then if you then cast this to disk here, which I've done, they would also be saving the volumes to disk as well. And then you would the whitewater solver would then fetch from this out node here. It would fetch both the candidate whitewater emission and the volumes for the simulation. What that meant was that you were saving those volumes to disk twice. Once when you were saving out the flip sim originally, and then again when you were caching out the whitewater emission particles, which is generally a good idea. So it just was wasting disk space. Because we now have that delayed load of the particles, we can have this separate node here, which is just a null. It doesn't really do anything except that says anything that if you read volumes from this node, because the flip simulation is set to delay load the particles, you won't actually load any particles when you're looking at the volumes. So what that means is we can output only points here, and these cache files on disk will be fairly lightweight because they only contain points. So that's why I can scrub through this because we've only got points in here, and the volumes themselves are going to be actually over here. This looks like I've actually got a velocity visualizer on here on the velocity field. But so we're seeing that same very lightweight representation for the flip simulation here that we're going to then load into the whitewater solver itself. And then the other new feature on the whitewater source is we can now distribute by dividing up a camera frustum. So if we look at this, we get a view of this from overhead. we're actually dividing up the camera frustum, so we've got 4 divisions in the x-axis, and each one of these slices of the frustum will do its own emission, and then you can distribute that across different machines. And you can do that in the x, y, or z axis along the frustum. And so, just to give an example of that, a bigger example of that river simulation that we saw, this is actually how we did it. We actually did it along the z-axis, so each of these different colors was simulated on a separate machine, and you can actually get another overview of this. So we only generated whitewater in the camera frustum to begin with, and then each of these different colors shows the different machines where it was being simulated. So then finally, if we go look at the whitewater sim itself, the interesting features here are we'll see that before the whitewater emitter so the whitewater emitter basically goes to this out node here. So it goes and gets, in this case, cached whitewater emitter particles. And the whitewater solver used to point at that same node, and it would then go fetch those volumes, resample them into DOPS fields, because we would then use the DOP gas particle advect node to do high quality, very accurate particle advection, which was required for the really accurate simulation of whitewater. With Houdini 15, all of those higher order advection routines have actually been moved into VEX, and they will work with both DOP fields and with SOPs. So what that means is we can actually fetch or work with the data directly from SOPs without doing any resampling into the DOPS fields in the first place. So that's what this import volumes into DOPS option here does, and by default it's off. So the VDBs that are being loaded into this null right here, and being delay loaded, so no particles are being loaded, they're operated upon directly using VEX from within the whitewater solver. So what that does, that just avoids that resampling operation, which was slow and took up extra memory, and just makes the whitewater solver more efficient when dealing with these large-scale sims. And so finally, just to show what this looks like with that, with the compressed fluid preview option that I was describing earlier, just as a way to sort of have a good idea of where the surface is going to be and put whitewater on top of it. This has the whitewater solver's preserve foam option on, which is why you get these kind of very sharp, swirly foam things at the end here, because it's essentially boosting the lifespan of any particles that are close to other foam particles. So you can turn this off if you don't want all these little layers, little swirls of foam here. So one thing I forgot to show is just where these new higher order advection operations live. So if you look at pop advect by volumes, which is an older node, it's been around for a while, but there's these advection methods here, and this midpoint RK3 and RK4 are all the higher order advection operators that are new for Houdini 15 and written in VEX. And if you want to go even lower level than that, there's a VOP that actually provides those operations and calls the proper VEX code. And we can, with these input tabs, you can actually go reference SOP data directly. So internally to the whitewater solver, this is what's going on, is we're referencing these SOPs directly and then calling those higher order advect operations within VEX. So finally, I'd like to go through some flip solver enhancements to the actual solver itself, and also some workflow enhancements that are around some new additional outputs that we get from the solver. So first off, we have a distributed pressure solve, which I'm not going to go into much detail because, as I said, we're going to have an entire masterclass on distribution. But it's what lets distribution work for tank sims like one you might see here. We've got a new swirly velocity kernel. That's basically a new way for transferring the velocities from the flip particles to the underlying fields or grids that are used for things like the pressure solve, and we'll talk about where that might be useful. We've got some new shading attributes that are output from the flip solver, and that's actually what you're seeing in this video here. Some shading, some render time shading and displacement being done based on vorticity from the flip simulation. And then finally, there's a new set of shelf tools specifically designed for creating viscous fluids. Okay, so let's look at some of those new enhancements to the flip solver in more detail. First off is the distributed pressure solve, which again I won't go into much detail on, but it's this option here. Before, our distribution worked for things that had a very consistent flow, like a river or waterfall, but you really couldn't do tanks. So where the pressure that was keeping the fluid incompressible needed to be solved for the entire tank at once, even if slices of that tank were running on different machines on the network. So that's what this distributed pressure solve option does, is it actually makes that pressure solve work across the entire set of machines that are operating on the same simulation. And that's why we don't have any seams between the fluid that's coming from the different slices of simulation. So the next addition we have is on this volume motion tab, this velocity transfer option here, and you have what's called the splashy kernel and the swirly kernel. Those names are really mostly descriptive. So splashy gives more sort of noisy, splashy, ballistic look, typical flip look, and the swirly kernel does a good job of keeping lots of vorticity and angular motion in the simulation, but keeps a smoother surface. And we'll quickly look at what those how those different kernels work and why you might want to use one over the other. So Flip is a hybrid solver, which means that it has particles and background grids or fields that we've talked about before. These are the surface fields and velocity fields that we're using in the fluid compression and surfacing and that sort of thing. So we have to, at the beginning of every time step, we transfer attributes like velocity from the particle to that background grid, do all sorts of processing there, and then transfer from the grid back to the particles. So in a hybrid solver like this, it's a very common set of operations. So this is, if you ever looked inside the flip solver asset, this is a few of the nodes you will have seen in there. This is the particle to field DOP microsolver, which is a single DOP that just takes care of transferring, in this case, the velocity attribute to that background velocity field. And then this is just a null. As a placeholder, we assume we do all sorts of pressure solves and advection and interesting fluid stuff, and then we transfer from the velocity field back to the particle attribute. So if we hit play here, so this is a sort of common flip layout. This is just in 2D, but you've got sort of an oversampled set of particles right around the edge of the fluid, and then an unevenly distributed set of particles within the fluid. So this is what a common flip simulation will look like. And then we've just got a procedurally generated, this is actually curl noise, to give us some nice swirly velocities on top of it. And if we hit play, we'll see that over time we lose all of our angular momentum. We're losing all these nice vortices that we had. And nothing is moving here. All we're doing is continually transferring the velocity from the particles to the grid, and then from the grid back to the particles. And just doing that operation will result in a loss of angular momentum. So this is what's called a particle and cell transfer. And Flip is actually a technique designed to overcome this limitation. So what Flip actually does is, instead of transferring the entire grid back to the velocity, it just transfers any change in those grid values from before all the pressure solve and everything else back to the flip particles. And that the velocity smoothing parameter within the flip solver is what determines how much of the resulting particle velocity is transferred from the grid and how much of it is left over from the previous particle attribute. So, from that delta. So Flip is good at maintaining the angular momentum, but it introduces some noise. So there's some clever recent research out of Disney that has created something called the affine particle and cell method. So if we turn on this preserve angular momentum option here on the field to particle node, we'll see that we keep all of our vorticity. So all of these little vortices and all the angular momentum we maintain it even though we're doing a full transfer from the grid back to the particles every frame. So what this does is it keeps all of this nice angular momentum like flip does, but it avoids any of the noise that comes in to the flip transfer, especially at the surface. So why would we want to use this? Mostly for very viscous simulations or small scale simulations where any noise can be really disturbing. So if you're trying to simulate something at a very small physical scale, any sort of noise or ballistic noise at the surface can be a little distracting. So that is this APIC method, this affine particle cell method, is the swirly kernel that we were talking about before. So just to show what this looks like in action, the top video here is the flip method, the traditional flip method, and this is the splashy kernel, and the one below here is using the swirly kernel. And you'll notice it maintains about the same amount of angular momentum here, but the surface itself is just sort of much smoother. You have less surface detail, less kind of noisy surface detail, like you do up here in the flip side or the splashy side. But for smaller scale simulations and viscous sims, this can be a really nice look, and it was tough to get without this new velocity transfer method in Houdini 15. So the other attributes we wanted to look at were some of these output attributes now that can be used for surfacing and in particular for shading. So there's this new vorticity tab here, which adds a vorticity attribute to the flip particles. And this preservation rate basically says how much of that vorticity per particle should remain after at the end of a second. So 10% in this case of the vorticity measured will still be there a second later. And so it's a decaying value, in other words. So what this lets us do, if we look at what this simulation looks like with vorticity. So this is a visualization of vorticity here. So you'll see that there's kind of this decay here. Everywhere that there's some interesting motion, there's sort of retains that vorticity attribute for a few frames at the very least, or maybe a second or two. So you can start to do some interesting shading and that sort of thing based on where there was interesting swirling motion within the fluid. And I showed this earlier, but so rendering with this vorticity attribute here, you get this sort of cloudy, look where there might be sort of micro particles or any sort of like tiny little bubbles or something. This is probably a little exaggerated, but it's kind of an interesting additional look for the shading. And the way we get that into the mesh is when we're doing our surfacing. For the transfer, vorticity is one of the default attributes that comes across from the particles to the mesh. So by the time we render this, we actually look at it here. I've got a visualizer here. This is the vorticity on the mesh itself. So it's actually got a vorticity attribute. And this can be used in conjunction with another attribute, which is this rest field, or rest attribute, I'm sorry. So it'll actually create the solver will output a rest attribute on each of these particles, which is at a given frame where the particle is in world space, and then that rest attribute will actually travel with the particle until it's reset every, in this case, 40 frames. And we actually will have two different attributes, a rest and a rest2 attribute, that are offset between each other, and they're constantly being refreshed, so that you can use because essentially over time, as the fluid swirls around, those values start to become all sort of messed up together, and they become less useful. So this is an idea that's very, if you've ever used the rest fields in the Pyro solver, this is exactly the same idea, to transfer around a rest value for particles and then reset them every certain number of frames. And so this can actually be used to do additional sort of surface displacement or texture mapping, or anything where you want to actually put some sort of procedural or lookup based additional attributes or render time attributes onto the surface itself. So the new shaders well, there's an addition to the liquid shaders that basically let us use that. So this vorticity to diffuse intensity is what maps from the minimum and maximum vorticity values. It just is a multiplier on this diffuse intensity, and so that's what you saw in that previous render. And then additionally, we've got these what are called vorticity waves. And so what this will actually do is apply a small amount of displacement everywhere that there is a certain amount of vorticity, and that will use those rest fields so that the displacement tracks with the surface. So let's look at what that renders like real quickly. So this is an opaque rendering actually. This is the same liquid shader. I just turned refraction off. So you can see in these areas where we've got lots of sort of vorticity and spinning around, we've got extra little kind of micro displacement going on that gives us this nice extra level of detail. These little things that kind of shine in the light, and we also are changing that diffuse intensity. So if we compare this to the same, let's just get a particular frame. If we look at this without those values, so this is the simulation without that extra shading. So you've still got a lot of detail, but there's just this extra little layer of, like for instance right here and sort of back in here, you've got just this kind of extra level of displacement going on that I think can, for certain situations can add a certain extra level of surface detail that can be nice. And finally, just to show what that shader looks like. So this is the part of the shader that does that that displacement. So you'll see it's using both the rest and rest2 attributes to create some noise, and then it's blending between them according to this rest ratio and rest2 ratio, which is essentially how long it's been between the last time that the rest fields or the rest attributes were reset, and how much of it should be used. So it's generating a certain amount of displacement from the rest value and a certain amount from the rest2 value, and then blending between the two. And then vorticity is run through a ramp here and multiplies to control the overall amount of displacement we get. And again, this is a very common. This is very similar to what happens in the Pyro solver if you're applying any sort of render time displacement or render time noise based on dual rest fields. And so finally, let's look at the new viscous shelf tools. So these are a set of tools that encapsulate some functionality that's been available through the viscosity solver within the flip solver, but it adds some shelf tools here that make it easy to set up a mapping between temperature and viscosity. So you can do freezing effects and heating effects, melting effects, that sort of thing. And a lot of that's encapsulated in this gas temperature update node here that we'll go through in just a second. But so this is, for instance, the melt object. This is an example created with that shelf tool. And if we hit play here, we'll see that we've got a viscous sort of set of particles, and then as this heated rod moves through it, it melts the object by essentially mapping everywhere that it gets really hot to a low viscosity value. And then you can actually see there's some temperature diffusion going on here. So the temperature is actually, or the heat is actually diffusing out through the particles, which is sort of what lets this whole object melt. So if we look at the controls here, this is what's this temperature diffusion option here is what's controlling how quickly the heat will diffuse throughout the particles. The heating volume here, this is actually where we get the temperature in the first place. So this is part of this. This is one of the shelf tools that will set up this sourcing of a heat object. So if we go to what this looks like here, you can see that there's it's a little hard to see, but there's a small you can see there's a small dense layer here that is the temperature, that is the heat basically. And so this transfer is essentially from that volume here into these particles to make them hot, and then it will diffuse out across the particles. And if just to real quickly show the difference, if you turn that diffusion off, what you'll get is something that looks more like this. Whoops, I'm sorry. This is one with no diffusion. and it actually just sort of cuts right through the particles, but the heat isn't diffusing any at all outwards. So it just kind of makes a very small cut through the viscous fluid in the first place. And so just to show a sort of more production-ish, although it would be kind of a disturbing production example, is showing this pig melting here. So again, this is a cool object that is falling onto this grate, which is heated, and then melting and falling through onto the ground below. And you'll see on the right here, the temperature diffusion is turned on, which is why the heat spreads throughout the object and melts everywhere. Whereas here, you get a much more contained sort of melting effect with the temperature diffusion off. And then this is just showing the lava emit tool, emit lava here. And so we've got just a kind of noisy emitter up here, and it's dropping lava which is on top of the pig, which then cools off over time. And the most important value here is actually this cooling rate here, this outer cooling rate, which is how quickly the surface of the lava cools off. And if we look at some different settings for that, so this is with a fairly slow cooling. You'll see that it takes a much longer time for the object to get less viscous, to harden essentially. And then this is the one that we were just looking at, so it's sort of in the middle. And then you can go where it cools off fairly quickly, and you'll get sort of a lava hat for the pig. And this, you can also cool the interior of the fluid more quickly if you want an even faster cooling rate than this. And so just to show some sort of higher res examples of that. So this is the same idea, just it's cooling here as it sort of sits longer, and the heat is actually affecting the shading as well over time. And then just to finish where we started, this is our crag character walking through some lava, and you can see it's sort of sticking to his hammer as he moves it through the fluid, and then again when he pulls it out at the end. And thank you for listening. That's all I have on this class today. Thanks very much.